Today I'm going to be solving problem 7.11 from the book Introduction to Electrodynamics by David J. Griffith. The problem states a square loop is cut out of a thick sheet of aluminum. It is then placed so that the top portion is in a uniform magnetic field and is allowed to fall under gravity. If the magnetic field is 1 Tesla, find the velocity of the loop as a function of time. How long does it take in seconds to reach, say, 90% of the terminal velocity? And what would happen if you cut a tiny slit in the ring, breaking the circuit? So, due to the motion of the loop going through the magnetic field region of the EMF induced, the equation will be E is equal to the magnetic field times length times velocity. We also know an induced EMF in terms of current, which is E is equal to current times resistance. Setting these two equal and solving for I, we can get the current is equal to the magnetic field times length times velocity over resistance. So, since we're dealing with forces, we have to find the forces that are acting on our square loop. One of the forces is magnetic force, which is governed by this equation. Force is equal to B times I times L, where we can substitute this I into here to get the equation. The magnetic force, F mag, is equal to the magnetic field squared times length squared times velocity over resistance. So, the magnetic upward force is balanced by the gravitational force acting on the loop. So, using forces, force of gravity minus the magnetic force is equal to net force. Substituting these in with the proper variables, F of g becomes mass times gravity. F mag becomes what we had written on top. And F net becomes mass times acceleration, but written as dv dt, change in velocity over change in time. So, at the instant the loop moves with terminal velocity, the upwards force is balanced with the downwards gravitational force, meaning we can get rid of this, setting that equal to 0, and setting Fg is equal to F mag, meaning mass times gravity is equal to all this. And solving for terminal velocity V, we get the following equation. V of t is equal to mass times gravity times resistance over magnetic field squared over length squared. So I'm going to set this as equation 1 because this is the terminal velocity equation. Now we have to solve for velocity. Going back to this equation in the very beginning, solving for velocity means we need to integrate dv on the left with v and factor everything out and find the formula. So starting with that, I'm going to write times v is equal to m dv dt. So we have one m here, one m here. So if I divide by everything by m, I can cancel my m's and get this to have an m where g minus magnetic field times length squared over m times r, v is on the outside, it's equal to dv dt. Here, I'm going to set all these variables as alpha, just so I can stop writing so much, and get the following equation, dv dt, where divide dv to both sides, dv over g minus ev equal to dt. So I'm going to set this as equation 2. So now that we have that, I can integrate both of those sides to solve for v. So by doing the integration, where I let g minus alpha v equal to u, du is then equal to 0 minus alpha dv. This becomes minus du. Alpha is equal to dv. Substituting what we found here back into equation 2, our formula then becomes I'm going to take a -1 over alpha out. du over u is equal to dt. So I'm going to do this integral where we get ln of u minus ln of a is equal to, going to take this alpha to the other side, negative alpha t, where ln of a here is just an integration constant that we're going to try to solve for now. We can write these two ln's as ln of u over a is equal to alpha t, where we can times this by e, times by e to get u over a is equal to e to the power of alpha, negative alpha over t, where we let u equal a e negative alpha over t, and plugging this u back into our equation, we're plugging it back in, we get g minus alpha v is equal to a e to the negative alpha t, and we want to solve for this when t is equal to 0 and v is equal to 0. Then this becomes g minus a times 0 equal to a1 times 1, where a is equal to g. I'm going to set this here as equation 3, and substituting that a we found a is equal to g back into equation 3, we get that g minus alpha v is equal to g e to the power of negative alpha t. Some more algebra steps. Alpha v is equal to g minus g e to the alpha t, negative alpha t. Substituting the g out. And solving for v, dividing everything by a, we get v is equal to g over a, 1 minus e alpha t. And remember, this is a, our alpha from before we set as the magnetic field squared times length squared times mass times resistance. So substituting that back in down here gives us the following equation. Velocity is equal to gravity over all that, magnetic field squared times length squared over mass times resistance times 1 minus e to the negative a over t. Where for this here, we can put all this together. Take the mr to the top, leave that to the bottom, to get v is equal to mgr over magnetic field squared, length squared, 1 minus e to the negative at. If we look at this here, we can actually see that we solved for this a little before. Where this is actually just v of t, given right here. I solved equation 1. So I can simplify this down even further to get velocity is equal to terminal velocity, 1 minus e to the power of at. I'm going to set this as equation 3. So once we have found this equation, we want 90% of that. So 90% of the terminal velocity, when v is equal to 0.90 v. So I can substitute this into here to get 0.90. Terminal velocity is equal to terminal velocity, 1 minus e to the negative alpha t. And getting rid of both v of t's, 0.90 is equal to 1 minus e alpha t. Doing some more steps, algebra steps. E to the negative at is equal to 1 minus 0.90. This becomes 0.10. E negative a sub t is equal to 1 over 10. Take the ln of this ln of this. Negative a of t is equal to ln 1 over 10. Take this negative to this side. A of t is equal to ln of 10. Solving for t is equal to 1 over alpha ln of 10. And from before, remember we have alpha. I said alpha as this again. We can substitute that back in to get the following expression for time. T is equal to mass times resistance over the magnetic field squared times length squared ln of 10. And I set this as equation 5, where it was given to us that the mass of the loop is the expression m is equal to 4n a times L, and R was given to us as 4 times the length of alpha over charge sigma, where N is the mass density of the aluminum plates, A is a cross-sectional area, L is the length of the plates, and sigma is the conductivity of aluminum, where we then substitute all this back into equation 5 here to get the following equation. 4 times length over this simplifies down to 16 n p over magnetic field squared length ln of 10, where I set 1 over sigma as that because there's a relationship between them. Now that we found this is all equal to time, where we have the appropriate values I found online, which is equation to the side. The mass density of aluminum is N is equal to 2.7 times 10 to the 3 kilograms per meter cubed. Resistivity of aluminum P equal to 2.8 times 10 to the negative 8 ohms times the mass meters, and the magnetic field strength B is equal to 1 Tesla is given, where I'm going to substitute all these back in to equation 6 right here to get the following. T is equal to times 2.7 times 10 to the third, 2.8 times 10 to the negative 8 over 1 Tesla squared ln of 10 to get the following. Time is equal to 2.785 milliseconds. So we found that T, but then we're also going to solve for terminal velocity. Back to equation 1 that I derived here, and see how we have R and M again. I can substitute those values that I found for it, which equation 1 will become 4N AL times 4L over A sigma times gravity over the magnetic field squared times length squared. Again, gonna simplify all this down to get 16 NGP over B squared, where N was the mass density of aluminum, G is gravity, P is the resistivity of aluminum, and B is the magnetic field strength. Values here again. So I'm gonna plug all that in to get the following. 16 times 2.7 times 10 to the third times 9.8 times 2.8 times 10 to the negative 8 all over 1 Tesla squared, which gives me 0.01185 meters per second. I'm going to convert this down to centimeters, which I would just multiply 100 centimeters per meter to get 1.2 centimeters per second for the terminal velocity, and this one was for the time.